For a long time, we've had a fundamental gap in our understanding of black holes. We know they aren't permanent, that they must die somehow, but the exact physics of their final moments, especially for the most extreme black holes, has been a real mystery.
So how does a black hole truly die? It's honestly one of the deepest questions in physics, sitting right at that messy intersection of gravity and quantum mechanics. What we're going to do here is walk through a recent study that gives us a crucial new piece of that puzzle. Our goal is pretty straightforward. What does this research actually show us? And just as important, what are its limits?
All right, so the baseline understanding, the one we've had for decades from Stephen Hawking, is that black holes leak. They're not completely black. They give off this incredibly faint thermal glow called Hawking radiation. And over immense timescales, this causes them to lose mass and eventually evaporate. That's the standard, semiclassical picture.
But that standard picture starts to get really fuzzy under very specific extreme conditions. What happens when you have a black hole that's spinning as fast as it possibly can? This makes it incredibly cold, balanced on a knife's edge of stability. In this near-extremal state, our usual equations just stop giving us reliable answers.
And this is exactly where the new physics kicks in. In that finely balanced state, the usual rules of gravity take a back seat, and the strange, subtle rules of quantum mechanics become the star of the show. This is the specific gap in our knowledge that a team of physicists decided to tackle. So let's dig into the exact question they set out to answer.
The researchers focus squarely on these black holes living on the brink of stability, hoping to address some key problems with our current models.
So here's what was at stake. The standard theories, the semiclassical ones, they just don't work at the super low temperatures of these black holes. Now, we did have some quantum models, but they were mostly for simplified, non-rotating black holes. The big problem with that is, in the real universe, black holes spin, and that rotation is a critical ingredient that changes everything.
So that leads us to the core question, the very specific, narrow target of this research. How do quantum mechanics and rotation work together to change the final moments of a black hole's life? That's the challenge they took on. Now that we understand the question, let's look at how they actually designed a model to answer it.
To get a handle on such a complex problem, you can't just dive in head first. The researchers had to develop a very clever theoretical model.
This diagram really shows their approach perfectly. They basically split the problem in two. You have the far horizon region, which is the area far away from the black hole. Out there, the good old classical laws of physics work just fine. But then you have the near horizon region, this deep quantum canyon right at the event horizon itself. And for that area, they needed a whole different toolbox, a specialized quantum theory to capture all the wild fluctuations going on.
So breaking it down, here was their process. First, they isolated the unique physics of that quantum throat. Second, they applied an effective theory that's known to work in these kinds of situations. The third step was the really tricky one. They had to mathematically stitch that inner quantum region to the classical outer region. And finally, once they had this complete combined system, they could calculate the rate that energy and particles would actually escape.
And this is a really important point to keep in our back pocket. This is a theoretical model, and it's designed for a very specific scenario, those near-extremal spinning black holes. That means its predictions are precise for that case, but we absolutely cannot turn around and make broad claims about all black holes. With that limitation in mind, let's look at what they actually found.
What emerged from all these calculations was a pretty significant and surprising tweak to the story of how a black hole dies.
But before we get to the main result, we have to understand a really cool concept called superradiance. With a spinning black hole, it's possible for a particle to just skim the edge and get flung away with more energy than it came in with. It's literally stealing a tiny bit of the black hole's spin energy. This cosmic slingshot effect is absolutely crucial to their findings. And here it is, the big takeaway, laid out right in this table. The standard, semiclassical model predicts a certain decay rate. Then, previous quantum models for non-spinning black holes found that quantum effects already slow things down a bit. But now look at this new study. When you include both rotation and quantum effects, you get an even more dramatic slowdown. That fraction, -8/21, is a significantly slower fade-out than any model before it had predicted.
And you can see it perfectly in these graphs from the paper. On the left, in a high-energy situation, the classical prediction in orange and the quantum model in blue are pretty similar. They almost agree. But now look at the plot on the right. This is our low-energy, near-extremal case. See how that blue quantum curve just dives?
It completely breaks away from the classical model, predicting a much, much lower rate of energy emission. The quantum reality is just fundamentally different.
So what's causing this? Well, it's this incredibly delicate balancing act. You have quantum effects that are trying to leak energy out. But at the same time, the black hole's spin, through superradiance, is actively pulling some energy back in. These two opposing forces nearly cancel each other out, and the result is this much slower net evaporation. So now that we've seen the data, it's just as important to understand what it doesn't show.
To really understand these findings, we have to be super precise about what this research can and cannot tell us.
So let's be crystal clear. This model is not a complete theory of quantum gravity. It doesn't claim to solve the famous black hole information paradox. It also only describes this one specific type of black hole, not all of them. And maybe most importantly, this is a theoretical calculation, not a direct observation of this effect out in space.
And the researchers themselves are very careful with their words. This quote, paraphrased from their abstract, emphasizes that quantum corrections may affect these rates, leading to a slowdown. That kind of careful, precise wording is the hallmark of good, honest science. So with that nuance in mind, where does this research fit into the bigger picture?
Well, this study represents one more important, concrete step on the very long road toward a unified theory of physics.
The reason physicists find this so significant is that it makes our models more realistic. Black holes in the universe spin. So, by successfully including rotation in a quantum framework, this study adds another solid brick in the wall of a theory of quantum gravity that theorists are trying to build.
And of course, like all good science, answering one question just opens up a dozen more. This result pushes us to ask deeper questions about the complex dance happening between a black hole's spin, its electrical charge, and the quantum foam of space-time itself.
So, after going through the objective, the methods, the findings, and all the limitations, let's bring it all together for one final measured conclusion.
What we can responsibly say is this. This theoretical model gives us strong evidence that for a very specific class of black hole, the coldest, fastest spinning ones, the end isn't some rapid decay. Instead, it's an incredibly slow fade into nothing, a final act governed by a delicate and beautiful dance between the quantum world and the immense power of cosmic spin.